In this video, we introduce our CVPR24 work, Mask Clustering, View Consensus-Based Mask Graph Clustering for Open Vocabulary 3D Instance Segmentation. 3D instance segmentation is an essential task for robotics and AR, VR applications. However, current 3D instance segmentation models lack fine-grained segmentation ability, primarily due to the scarcity of annotated 3D data, which is costly to obtain. In contrast, 2D instance segmentation has achieved excellent fine-grained segmentation capabilities. Therefore, it's natural to utilize the well-established 2D models to help 3D instance segmentation. To leverage 2D models, we input a reconstructed point cloud alongside a posed RGBD scanning sequence. We use 2D models to extract instance masks from images and then merge them into 3D instances. Yet, a key challenge in this 2D to 3D approach is the inconsistency of 2D instance IDs across frames. For example, the IDs for the same object, like a piano, differ between frames. Previous efforts, such as OVIR3D and SAM3D, have delved into this direction. To decide if two 2D masks belong to the same object and should be merged, they first back-project the masks into point clouds and then check how much they overlap. If there's enough overlap, they merge them. However, this metric relies solely on two frames, not the entire scanning sequence, leading to limited robustness. Inspired by the classic bundle adjustment algorithm, we propose using multi-view verification to determine whether two 2D masks should be merged, improving global consistency. To utilize the entire sequence for verification, we introduce a novel metric, the view consensus rate. This rate is defined as the proportion of frames that support merging these two masks. Specifically, for the blue and red masks shown here, we initially project them back into point clouds. They correspond to the left and right sides of the same piano. Now, let's check each frame in this sequence. In this frame, the 2D model segments the piano as a whole. Both the blue and red point clouds are contained by the green mask, so this frame supports the merging. Moving to the next frame, the 2D model mistakenly segments the piano into two masks. The blue one is contained by the orange mask, while the red one falls within the green mask, opposing merging. In the rightmost frame, the 2D model segments the piano as a whole, but only the blue point cloud is visible in this frame, so this frame cannot contribute to the vote. Conversely, in the leftmost frame, the 2D model segments the piano as a whole again. Both point clouds are contained by the green mask, supporting merging. Hence, 3 frames participates in the voting process, 2 in favor and 1 against, resulting in a support rate of 2/3. Given the view consensus rate, we now introduce the full pipeline. For clarity, we only visualize 3 objects in the figure. First, we run the 2D instance segmentation model on the entire sequence and extract all 2D masks. To enhance global consistency, we construct a graph where each 2D mask serves as a node. For the 2 masks corresponding to the left and right sides of the same piano, we've just computed their view consensus rate. Since it surpasses a certain threshold, we connect them with an edge. We repeat this process for all nodes, establishing edges accordingly. Next, we use classic graph clustering method to group masks into several clusters, with each cluster representing a 3D instance. Within each cluster, we merge the mask point clouds to obtain the final 3D instance mask. Here are the instance segmentation results generated by our method for a 2-story building in Matterport 3D. We can also query instances with text like, white clothes on the sofa chair. You can see that the pillows, pictures on the wall, items on the nightstands are clearly distinguished. Let's go down to the first floor. The curtains, carpets, pillows, bottles in the kitchen are also clearly separated. Our method shows an impressive fin-grained segmentation. On the challenging ScanNet++ benchmark, our method surpasses previous state-of-the-art significantly by more than 4 AP and 8 AP25. In summary, we create a robust and efficient tool for open vocabulary 3D instance segmentation. Technically, we utilize 2D instance segmentation models and employ multi-view verification to merge 2D predictions. Here is the link to our GitHub repository. Thanks for your listening.